Hello, everyone. Today I will present the suffix string. So for building a suffix string, I will alternately choose to use the suffix array and LCP. So firstly, I will talk about suffix array. So here's the outline. First, I will talk about a suffix array, then talk about general construction strategy, and then initialization. Next is the sort double cyclic shift, and then updating classes and for algorithm. So construct a suffix array. First, we need to input a string s and then output all suffix of s in lexicographic order. So what is lexicographic order? Actually, it's from the aspect of alphabet. So we assume the alphabet is ordered. That is, for any two different characters in the alphabet, one of them is considered smaller than another. For example, in English, we can see A less than B, B less than C, and so on, and less than Z. And here we assume the alphabet size is constant. So here we have a definition. Assume string S is lexicographically smaller than string T if S is not equal to T, and there exists such I that I equals to the range of 0 and the length of the string S. And we assume the previous I minus 1 characters for string S and string T are same. And even for I equals to the length of S, if we want to conclude S is a prefix of string T, then we can use this in equation. Let's see some example. So for example, AB less than BC, and here we determine this relationship between two strings according to the first character. It's A and it's B, and we index the first index is 0, and also for ABC less than ABD, we can see both strings have same two characters AB, but yeah, the third one is different, and C is less than D, so we can conclude ABC less than ABD at the index I equals 2, similar for this one. Let's take example about the suffix array. So giving a string S equals to AB, AB, AA, then we can get all the suffix in lexicographic order, such as for the length 1, we can see we have A. For length 2, we have AA, and also we have AB, AA, AB, AB, AA, BAA, BA, BAA. So we have different lengths of suffix. Here we need to mention some prefix rule, avoiding prefix rule. The first one is inconvenient rule. So if X string is a prefix of T string, then we can conclude S string is less than T string. And we also assume the character $ smaller than all other characters to the end of all strings. And third, if S is a prefix of string T, then S differs from T string in position at I equals to the length of string S. And we can conclude this S string is less than T string. For example, in this example, we have S string AB, AB, AA, and we have S prime with $sign at the end of the string. To get the suffix in lexicographic order, since we assume $sign is the smallest one, so $sign will be the first one in the order, and others same with the previous page order. And when we remove the $sign, the suffix order actually do not change. So how much spaces will be used when storing all the suffix array? We can know the total length of all suffix can be summed by this equation. So the total one for the sum is theta, the length of S string square. But we can know the disadvantage is storing them all is too much memory. How can we reduce the storage memory used? We can propose a method to store the order of suffix in big O of the length of string. And the suffix array is this order. That's why we introduce the suffix array here. Let's see this example. So here, suffixes are numbered by their starting position, like AB, AB, AA, $sign. You start with 0 from A character, and AB, AA, $sign is start at the 2, so we can see it's from here. And we can define a suffix array is the order array, is an empty array here. So for the $sign at the end of the string, the corresponding index assigned with 6. And for this A correspond to 5, and also 4, 2, 0, 3, 1. Okay, now you know how to store the suffix array, but how to construct it. So we will talk about the algorithm to construct the suffix array. So before that, we will illustrate the general construction strategy. So we will use sorting cyclic shift. We can see AB, AB, AA, forms a cycle. So we can in this sorting cyclic shift, we can see the trend. So start from A, then we can have A, B, AA, suffix. Then go to start with B, so B, A, B, B, no, B, A, B, AA, A. And then start with A and end with AB, and so on. So the first column we got from the cyclic shift. And then we can order the first column suffix into the second column. So the second column is ordered suffix. So if we remove the characters behind the sign dollar, then we can get the third column of suffix, which is ordered and presented in previous slide. So here is the lemma. After adding to the end of string s character $, which is smaller than all other characters, sorting cyclic shift of string s and suffixes of string s is equivalent. So for partial cyclic shift, we define substrings of cyclic string s are called partial cyclic shift of string s. So partial cyclic shift example we can say here. Like we assume the cyclic shift length is 4, then we start from A. So we have A, B, A, B, then BA, BA, and so on. So the general strategy, we start sorting single character of string S. Then cyclic shift of length L equals to 1 sorted. And then we will go through a while loop. And the terminal condition is L less than the length of string. Sort shift of length twice L. So if L greater than the length of string S, cyclic shift of length L sort the same way as cyclic shift of length the string S. So let's say this example. And for the length of 1, according to the cyclic shift, so we can get this order from previous suffix array. And here is the index order. And also, if the length is assumed to be 2, then we can get this column of suffix. And the order doesn't change. Similar for the length of 4. And also for the length of 7. And if we mark the characters behind sign dollar, so we can see this column of suffix are the ordered suffix for this string S. And let's see the third part is initialization for constructing suffix array. So sorting single characters, we assume the alphabet sigma is a constant, so has sigma different characters is a constant. And we will use counting sort to compute order of characters. So here is the sorting characters procedure. And let's go through it. So first we need to define an order array with size of string, and also need to define a counter, start with 0, and then we will go through some loops. Then we will return the order finally. So let's see the lemma. The running time for the sort characters here is big O, the length of string plus the size of alphabet. So the proof is we know this is the running time of the counting sort for string S items that can take the alphabet size, different values. And here we will define the equivalence classes. So CI is a partial cyclic shift of length L starting in I, and Ci can be equal to Cj, then they are in one equivalence class. Compute class I the number of different cyclic shifts of length L that are strictly smaller than Ci. And if Ci is equal to Cj, then we can conclude class I and class J are same. So let's see this example. So first we will start from the smallest character, which is the $sign, and the order corresponds to the starting index. And we assign a new class for the $sign. And the second one is character A, which is at the initial position in the constraint. And A is different from the previous class. So we will assign new class for A at the position 1. Similar for the third character, which has been put at the position 2, but A is similar, but A is same like the previous A, so they have the same class. So and so on for other characters, we will have the classes. Here, let's go through the compute character classes pursuit code. So at the beginning, we need to initialize an array for class, and then we initialize the order to each class. And then we will go through a for loop. And finally, we will get the class for the suffix order. So here's the lemma. The running time of computing character classes is big O, the length of string. And because they are only one loop with operations decided by the length of string. So after initialization, we will talk about how to sort doubled cyclic shift. So the idea is we define Ci is the cyclic shift of length L starting in I, and we have Ci prime, doubled cyclic shift starting in I. And Ci prime will be Ci and Ci plus L combined together. And so to compare Ci prime with Cj prime is sufficient to compare Ci with Cj and Ci plus L with Cj plus L. And here's the example. So we are giving the string. So we assume the length is equals 2, and we start I equals to 2, then Ci equals to C2, which is AB, and Ci plus L equals to 2 plus 2, so equals to C4, correspond to AA, and also Ci prime equals to C2 prime equals to ABAA, and which we can know is combined by AB and AA, so it's combined by C2 and C4. So for sorting pairs, first we need to sort by second element of pair, then stable sort by first element of the pair. So we can see here is the example, and the length is 2. So we can see from this cycle shift. So we start $A, but here it's not ordered, and we can see then how can we get the C prime? So we have this. So let's start from $A, and we put previous two characters AA here. So we got the C4 prime. Similar, we can get the C3 prime by put the previous two character here, and so on. We can get other CI prime. And we mark the yellow color for the first half two characters. And here we can observe those characters are not ordered. And we can see C2 prime and C0 prime. For the first half two characters, they are same. So when we order those suffix, we need to put these two in order close. Similar for C3 prime and C1 prime, they both have the BA at first half. So after order, we can see the dollar sign should be put there first. Then here's the ordered one. And we can also notice that C2 prime and C0 prime in order very close. Similar for C3 prime and C1 prime, their order also close. So for sorting doubled cyclic shift, the CI prime, which is the doubled cyclic shift starting in I, and CI prime is a pair of CI plus L. And we also have C ordered 0, C ordered 1, and so on until C order the length of string minus 1 are already sorted. Then take double the cyclic shift starting exactly L counted clockwise to the left. And then C ordered 0 minus L prime, C ordered 1 minus L prime until C order the length of string minus 1 minus L prime are sorted by the second element of the pair. Then we need a stable sort by first element of pairs. And here, counting sort is very stable. We know equivalent classes of single shift for counting sort. So here we list the pursuit code of sort doubled. So here we need to input the string, the length, the order, and the class. So first we initial the counter with size, the length of string, and also new order array. And we'll go through those group. And finally, we'll return the new order for the cyclic shift. And then see the lemma. The running time of sort doubled, it should be big O, the length of string, because the 3 loops in this procedure with the big O, the length of string operations each. So this can be done in linear time. Then we will go through the updating classes and full algorithm for the suffix array. So for updating classes, at the previous step, the pairs has been sorted. So go through them in order. If a pair is different from previous, put it into a new class. Otherwise, put it into previous classes. And here we will use pairs. So we know equivalent classes of element of pairs in the cycle shift previously illustrate. Now we see an example. So we are giving the string S, and we have the single cyclic shift classes here. And we have the CI prime, and also we have the pairs. Actually, it's the double cycle shift pairs. And here we have the new order, but here we need to update the classes according to the input and the pairs. So first, let's start from the $A, and the position is at 6. And for this one, we assign a new class 0 at position 6. And also for this $8, so the position corresponds to 5. And since these two, we compare these two, and the second $8 is different from the $A, so we will assign a new class here, 1. Similarly for AA at the position 4, so we will assign a new class is 2 because these two pair 1 0 and 1 1 is different. Similar for AB, we have the new class 3, and next AB. AB has the same class with the previous AB, so at position 3. Similar for C1 prime, BA is different from AB, so we assign the new class 4, but BA is same like the BA previous, so we still use class 4 here. And here's the passcode for the updating classes. The first we input new order and classes and length of L. So first the initial new order and new classes, and new class initialize with 0, then goes through this for loop and return the new class like we illustrated in the example. So the running time for updating the classes can be done in linear time because you see there is only one loop with big O, the length of string operations. So let's go through the final algorithm to build the suffix array. Previously, we have introduced 4 subcode, which is the sort single cyclic shift of string by this sort characters function, and then we need to compute the equivalent classes for the single cyclic shift of string. Use this compute character classes function, and then we go through a while loop. In this while loop, we have 2 functions. One is the sort doubled, used for sort the doubled cyclic shift of string, and according to the double cyclic shift of string, we can update the equivalent classes, and then we return the new order. Let's see the running time. So the running time can be the running time for constructing a suffix array is big O, the string length, log string length, plus the alphabet size, and it's easy to prove. So the initialization will cost in big O of length of string plus the alphabet size, and computing equivalent classes will cost big O of the length of string. And in the while loop, we will have a function sort, doubled, and also function update classes. Both of them will be done in linear time, big O of the length of string. And here, the termination will be L less than the length of string, because L will be updated by 2. That's why we use the log, the length of S iterations in total. So finally, let's see the conclusion. So we can build a suffix array of a string S in big O S, log S using linear memory. We can also sort all cyclic shift of a string S in the same time. And suffix array enables many fast operations with the string. And then we will talk about how to construct suffix string from suffix array in linear time. So you will be able to build a suffix string in total, big O, the length of string log, the length of string time. In this slide, we will continue to talk about how to construct the suffix string. And in this part, we will talk about the relationship between the suffix string and suffix array, and also how to compute the longest common prefix of the string. So for constructing a suffix string, we need to input the string S, and the output will be the suffix string of string. So the naive method will cost a big O of the length of string square to build the suffix string. But here we will talk about a more efficient way using big O of length of string log length of string. So the general idea is construct the suffix array in big O, the length of string multiplied by the log of the length of string. Then we need to compute additional information in linear time for the longest common prefix of the string. Then we will construct the suffix string from the suffix array and the longest common prefix information in linear time. So first, let's see the relationship between the suffix array and the suffix string. So we are giving the string $, and here we can see from the root node to the lift node, which correspond to the first character $, and here the number 0 correspond to the order number 0 here. And the second character is the $, which is in order in 1. And here is the path from the root to the leaf also is corresponding to this character, and so on. For 2, we can also find the corresponding path from the root to the left, and also for the third suffix, and also other suffix, we can find the corresponding path from the root to the left. So for building the suffix string, we need to compute the longest common prefix. Here we define the longest common prefix, or we short for called LCP of 2 strings S and T is the longest such string U, that string U is both a prefix of string S and T. We denote by LCP string s, t, the length of the LCP of string s and t. For example, LCP for suffix ab, abc, and abc equals to 2 because their longest common prefix is ab. The length is 2. But for the suffix a and b, they do not have the common prefix, so the length is 0. And here, let's see the relationship between the suffix array, suffix string, and the longest common prefix. So let's see the first one. First one is from the node, from the root to the first leave node, $sign. And for the first two characters, the common prefix is the root, which is marked by the yellow color. And for the suffix $, and suffix $, their longest common fix is the urge A. Similar for 2 and 3, the longest common prefix is the urge A2. And for the suffix AB $, and AB $, their longest common prefix is ABA, marked by the yellow path. Similar, we can find for the suffix $, the common prefix is the root node, and for 5 and 6 suffix, their longest common prefix is BA. So here we define the longest common prefix array. Consider suffix array A of string s in the row form, that is A0 less than A1 less than A2, and so on until less than A. The length of string -1 are all the suffix of string s in lexicographic order. LCP array of string s is the array LCP of size the length of string -1 such that each I such that between 0 to the length of string -2 for I, we have LCPI equals to LCP pairs of AI and AI plus 1. So here, let's see the LCP array example. Let's see the LCP array example. So here we will do the pairwise comparison for two suffix element. First, let's see 0 correspond to the $sign, and compare the dollar with the $, then actually don't have the common prefix, so we assign 0 at the first element in the LCP array. Similarly, we compare the second suffix with the third suffix, and we found the longest common prefix is A, so the length is 1, so we assign 1 here. Similarly, for the following comparing, so we can have 0 and 2. So let's see the LCP array property. Here we have a lemma. So for any index I less than j, the longest common prefix between AI and AJ less than LCP of I and LCP between AI and AJ less than LCP of index j minus 1. So let's see the proof. So I and I plus 1, these two suffix has the longest common prefix AB, 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 and so if LCP between AI and AJ greater than LCP AI and AI plus 1, then consider the length of longest common prefix between A and AI plus 1 equals to K, and assume K less than 2. And if K equals to the length of AI plus 1, then AI plus 1 less than AI, so it's contradict. Otherwise, AJK equals to AIK, but not equal to AI plus 1K. If AJK equal to AIK, but less than AI plus 1K, then AJ less than AI plus 1, which is also contradictory. And if AIK greater than AI plus 1K, then AI greater than AI plus 1 is also contradictory. So for each index I, we compute the longest common prefix between AI and AI plus 1 through comparing AI and AI plus 1 character by character. So for each I, in linear time, big O of length of string, we can do the computation. We can do the computing. And big O of length of string different I, in total, the time will be quadratic time. So big O of the length of string square. So can we do it fast? So the idea is let H be the longest common prefix between string I minus 1 and its adjacent nested suffix in the suffix array of string S. Then the longest common prefix between Si and its adjacent nested suffix in the suffix array is at least H minus 1. So giving the string S, if we compare the I minus 1, J minus 1, these two suffix, then we can get the longest common prefix H equals to 2. Similarly, for I equals to 10 and J equals to 3, the LCP length is 1. So 1 should greater than H minus 1, which correspond to the previous increment. So the main ideas here, start by computing longest common prefix between A0 and A1 directory. Instead of computing the LCP A1 and A2, move A0 one position to the right in the string, then get some AK and compute LCP between AK and AK plus 1. We need to repeat until longest common prefix array is fully computed. So the length of LCP never decreased by by the length of string. So here's notation. Let ANI be the suffix starting in the next position in the string after AI. And let's see the example. So we are giving the string AB, AB, D, A, B, C. So for A0 and A1, the longest common prefix is AB. So compute LCP between A0 and A1 equals to 2 directory. And here, LCP AN0, AN1 greater than LCP A0, A1 minus 1, and A0 less than A1, then we can conclude AN0 less than AN1. So the LCP of AN0 is the next in order in AJ is also at least LCP between A0 and A1 minus 1. So the LCP of AN0 is the next in order. AJ is also at least LCP between A0 and A1 minus 1. And if the longest common prefix is B, then LCP AN0, AN1 greater than LCP between A0, A1 minus 1. And we can conclude A0 less than A1, then AN0 less than AN1. The LCP of AN0 is the next in order. AJ is also at least LCP AN A0, A1 minus 1. Then compute LCP AN0 AJ directory. So the algorithm will be compute LCP between A0, A1 directory, then save as LCP. The first suffix goes to the next in the string, and second suffix is the next in order. Then compute LCP, knowing that first LCP minus 1 characters are equal, then save as LCP. Then we repeat the process until fill the whole LCP array. So here's the pursue code for the LCP of suffix. We will input the string, and here we will go through the while loop. Finally, return the LCP. And we have the invert suffix array function to return the OPS, and OPS is array of size of the order. So we will use the POS array to install the order through this loop. Then we compute LCP array by input the string and order computed by last function. And here we also need to go through the loop through 0 to the length of the string. And finally, we will get the fully filled LCP array. So let's see the computing complex. So this algorithm computes LCP array in linear time, which is the big O of the length of string. And the proof is, so each comparison increase LCP once, but LCP finally always less than the length of string. And each iteration, LCP decrease by at most 1. And the number of comparison should be limited to big O of the length of string. Now we have introduced the suffix array building and how to compute the longest common prefix. Finally, we can build the suffix string here. For example, we are given the string AB dollar. Then we start with the root node, and the root node will be connected to the first leaf node with the dollar sign here. And with the suffix and the longest common prefix comparing, we can know the dollar string and $8 string both have the longest common prefix is the root node. So we start $8 from the root node. And let's compare the next with previous. So we can see $8 and $8 have the longest common prefix is A, but we need to build AA, so we need to create an eternal node through the edge A. And then we can compare $8 with ABA$, and the LCP for them is A2, so we can just start from this yellow node for the suffix ABA$. Similarly, for the these two suffix, the LCP is ABA. So we need to separate from the BA, create a new node to build the ABA$ suffix. So similarly, we can build BAA, but BAA has no longest common prefix with previous suffix. So we need to start from the root node. And similarly, they have their LCP is BA. So we create an eternal node after BA, and then build the BAA$ here. So we finished the train building through the ordered suffix and also the longest common prefix between pairwise suffix comparing. The summary. So this algorithm builds suffix array and LCP array at the beginning, then start from only root node, then group first edge from the first suffix. Then for each next suffix, go up from the leaf until longest common prefix with previous is below. Then build a new edge for the new suffix. So here we have a class suffix tree node and suffix tree node with parent. and we define the children, the string depth, and edge start and edge end in the code. And then we input the string and order and also the fully filled LCP array to the function stf from SA. And here, through this function with length of the string, then we can return the root. And also, we have the function create new leaf by input the node and string and suffix. And also we need to break urge through input node, the string and start and offset. So what's the time complexity for this algorithm? So actually this algorithm can be run in linear time, which is the big O of the length of string. And because the total number of urge in suffix string is the big of the length of string. So for each urge, we go at the most once down and also at the most once up. So we use constant time to create a new urge and also for the potential a new node. So the conclusion is we can build the suffix string from suffix array in linear time through the longest common prefix. And also we can build a suffix string from scratch in big O, the length of string multiplied by log of the length of string. Now let's see the application of the build suffix string in searching a pattern. So let's go through the basic ideas. So assume we have built a suffix string now, giving a pattern string, then how to search it in the suffix string. So first, starting from the first character of the pattern and root of suffix string, which is here, then do the following for every character. A, for the current character of the pattern, if there is an urge from the current node of suffix string, follow the urge. If there's no urge, print pattern doesn't exist in text and return. If all characters of pattern have been processed, that's to say, there is a path from root for characters of the given pattern, then print pattern found. So let's see this example, giving the string banana. So let's find the pattern NAN. And in this suffix string, the pattern ANN should be should consist of these two urge. And let's compare this picture with this algorithm on the left. So we start with the character n, which is correspond to this step for the current character of pattern. So if there's an urge from the current node of suffix string, follow the urge. So we follow the urge starting with n. And if there's no urge, print pattern doesn't exist. But actually, we found the n character, so we start this urge. And from here, we also found another n, which is the third character in this pattern, in this urge. So since all characters of pattern have been processed, and we found a path from the root to the given, from the root to the given node, then actually we found the pattern actually, NA, N, or if we are given NA, then we can also find the pattern NA through these two urge. And what's the searching time complexity? Actually, for any pattern with length of m, the searching time will be big O of n time. Let's see the second application of the suffix string used to find the longest repeated substring. So here I put the examples of the longest repeated substring for giving some strings. Like for this strings, the longest repeated substring is JEEKS, and for this one, it keeps repetitive a character, and for the third string given, which is conjunctive, and there's no repeated substring. And for this one, ABA, the longest repeated substring is ABA. And also for banana, the longest repeated substring is ANA. So let's see more details. So here we put this example for string ABA, and we build the suffix string here. So in this substring, we can find repeated substring like A, B, AB, BA, until AB, ABA, and the longest repeated substring is AB, ABA. And in this suffix string, one node cannot have more than one outgoing urge starting with same character. So we can see A, BA, BA. Actually, that's true. One node cannot have more than one outgoing urge starting with the same node. So if there are repeated substring in the text, they will share on same path, and that path in suffix string will go through one or more internal nodes down the train. So let's look at the longest repeated substring ABA. So it indeed goes through the internal node from the root node to the deepest node. So here, the longest repeated substring will end at the internal node. Actually, is here, ABA. Actually, this node is farthest from the root, and also called deepest node in the tree, this node, because the length of substring is the path of label length from the root to this internal node. So finding the longest repeated substring boils down to finding the deepest internal node. And what's the time complexity? So finding the deepest node will take big O of n, and n is the length of